Welcome back to the deep dive. So, usually when we sit down to talk about the absolute cutting edge of AI, you have this specific mental image.
Right. Oh, absolutely. The monolith.
Yeah, exactly, the God
Yeah.
model. Just this one single massive digital brain sitting in some heavily guarded server farm somewhere designed to just, I don't know, answer every single question in the universe.
It is the standard mental model. It's the whole one ring to rule them all approach.
Right. But today, we're unpacking a technical paper released by the Llama team at AI at Meta, and the title alone tells you they are going in a totally different direction. It's called the Llama 3 Herd of Models.
And that is such a deliberate choice of words. A herd.
Yeah.
It implies a collective. It implies specialization. And honestly, after really digging into this paper, which, by the way, for those of you listening, is incredibly dense, it feels like a major pivot point for the industry.
A pivot from what to what, exactly?
Well, we're moving away from the whole my massive model is bigger than yours competition and moving toward my ecosystem of models is smarter and more efficient than yours.
I like that. Though, to be fair, they did still build an absolute monster. We have to address the elephant or, I guess, the giant llama in the room.
Yeah, we do.
The flagship model in this herd is 405 billion parameters.
It is staggering.
It's massive. But the paper isn't just taking a victory lap about how big it is. It's really a blueprint. Our mission today is to explore how they coordinate that massive flagship model with the smaller models, the 8B and the 70B.
Because that's how you build a system that actually scales.
Exactly. So we're going to get into the architecture, this really unique data diet they used, and the absolute engineering nightmare of training on 16,000 GPUs simultaneously.
Nightmare is definitely the right word. When you read the infrastructure section, you realize pretty quickly that this wasn't just a software problem, it was a physics problem.
Yeah, we'll get to the melting hardware in a bit, but first let's talk strategy. Why a herd? If you have the money and the compute, why not just build the 405B model and, charge everyone to access it?
Because it really comes down to utility versus cost. Think about it like a construction company.
Okay.
That 405B model is your massive multi-ton industrial crane. It can lift literally anything. It has incredible reach, but it takes forever to set up and it costs a fortune to run every single hour.
Right. You don't bring in a massive crane to hang a picture frame in your living room.
Exactly. And that picture hanging tool would be the 8B model. The 8B is your cordless drill. Fast, cheap, runs on a battery. And for 90% of your daily tasks, it is objectively the better tool for the job.
But the 70B.
That's your forklift. It's the middle ground. Meta clearly realizes that if they want Llama to be everywhere, it can't just live in a massive, expensive data center. It has to be able to run locally on high-end consumer hardware.
So the flagship 405B exists to set the absolute ceiling for what the herd can achieve.
Yes, and as we'll dive into later, its main job is actually to teach the smaller models.
Okay, let's get into the architecture of this 405B beast, because I was reading the specs, and I kind of expected to see the trendy stuff. Everyone right now was talking about mixture of experts or MOE.
Yeah, where you break the model into smaller expert networks and only activate a few of them at a time to save on compute. It's very popular right now.
Right. GPT-4, Mixtral, they all use MOE. But Meta didn't do that.
They did not.
They stuck with a standard, dense transformer architecture. Honestly, that feels a bit retro. Isn't that just burning money?
They are definitely burning compute. With a dense model, every single parameter is active for every single token you generate. It is mathematically very heavy.
So why do it?
Stability. The paper is hyper-focused on this. When you are training at this scale, 16,000 GPUs working together, complexity is your absolute worst enemy.
I see.
Mixture of experts adds this whole layer of routing complexity. The system has to constantly decide which expert gets which data, and that can make a massive training run incredibly unstable. Meta basically said, look, we have the compute, we just want a training run that we know for a fact will actually finish.
So they traded cutting-edge architectural efficiency for pure reliability. Keep the engine simple, just make it enormous.
Precisely.
But they did tweak some things. I noticed they expanded the context window to 128,000 tokens.
Which is pretty standard for a flagship model today. It's like being able to hold a long novel in its short-term memory all at once.
But what really caught my eye was the vocabulary size. They bumped the vocabulary up to 128K tokens as well. For the folks listening, why does the size of the AI's dictionary matter so much?
This is a really elegant nuance. Older models usually had a vocabulary of maybe 32,000 or 64,000 tokens. By doubling it to 128K, you are essentially giving the model a much higher resolution map of human language.
How does that actually help performance, though?
It's all about compression. Let's say your vocabulary is small. If you encounter a complex word in, say, Thai or Hindi, the model might have to break that single word down into 4 or 5 separate fragments or tokens.
Because it doesn't recognize the whole word?
Exactly. So it has to process each fragment individually.
Which slows it down.
It slows it down and it eats up the context window. But with a massive 128K vocabulary, that complex foreign word might just equal one single token.
Oh, wow.
Yeah, so the model can process non-English text dramatically faster, and it packs a lot more actual meaning into that context window. It's a huge efficiency gain.
Okay, so they have this massive, reliable, high-resolution engine. Now they have to feed it. And this is where the numbers just get completely absurd.
The data scale is wild.
15.6 trillion tokens of training data.
It's almost impossible to visualize.
Ooh.
Just for context, Llama 2 was trained on roughly 1.8 trillion tokens. So this is an 8 or 9 times jump in sheer volume.
But look, anyone who has spent 5 minutes online knows the internet is mostly garbage. If you just vacuum up 15 trillion tokens of the open web, aren't you just building the world's most articulate troll?
The classic garbage in, garbage out problem.
Exactly.
Meta was very aware of this. The paper details a highly rigorous filtering pipeline. They didn't just scrape the web, they aggressively curated it. They used heuristics and built specific classifiers to strip out adult content, personally identifiable information, and just straight up low-quality gibberish.
And this is actually where the herd concept shows up really early on.
Yeah.
They use Llama 2 to filter the data for Llama 3.
Yes, they used the previous generation of their AI to act as the bouncer for the new generation. Llama 2 would read the raw text and assign it a quality score. If a web page didn't pass the Llama 2 test, Llama 3 never even saw it.
AI, bootstrapping better AI. But honestly, the real light bulb moment for me in the data section, and I think this is the crucial takeaway for anyone building models right now, is this concept they call annealing.
Oh yes, the annealing data. This is the secret sauce of the whole run.
Can you explain this? Because usually annealing is a term from metallurgy, right?
Mm-hmm.
Heating up metal and then cooling it down to change its properties.
Spot on. In metallurgy, you heat the metal to relax all the internal stresses, and then you carefully cool it to lock in its strength. Meta applied this exact philosophy to AI training.
Okay, how does that work?
The heating phase is that massive 15.6 trillion token run. You feed the model everything, Wikipedia, Reddit, massive web crawls. You are forcing the model to build a very broad, generalized understanding of the whole world.
Like giving it a broad liberal arts degree.
That's a great way to think of it. It learns a little bit about everything.
Yeah.
But if you stop the training right there, the model is a jack of all trades and a master of absolutely none.
Right.
So for the very final phase of training, we're talking just the last tiny fraction of a percentage of the run, they completely change the data diet.
The cooling phase.
Exactly. They cut out all the general internet noise. And they suddenly feed it an ultra-concentrated diet of high-quality, dense educational data. We're talking pure math, complex, curved, verified scientific papers.
Why not just train it on the good stuff from day one? Why wait until the end?
Because there literally isn't enough of it. High-quality, verified scientific and mathematical data is incredibly scarce. If you only trained on that, the model would run out of reading material in a day.
Ah, I see.
You need the massive volume of the open web to teach it how to speak and reason generally. Then you use the scarce, high-quality annealing data right at the finish line to radically sharpen its logic.
And the results speak for themselves. The paper notes that on the GSM-8K benchmark, which is a test of grade school math performance, jumped by 24% just from this final annealing phase.
A 24% bump at the very end of a training run is unheard of. Researchers usually fight tooth and nail for a 1 or 2% gain. It essentially proves that the order in which you present data to an AI matters just as much as the data itself.
It's amazing. Okay, so we've got the simple architecture, we've got the curated data diet. Now we have to talk about how they actually ran the code. The infrastructure.
The hardware nightmare.
16,000 H100 GPUs running simultaneously. And to make this work, they use something called 4D parallelism, which sounds like a buzzword, but it's actually fascinating.
It is the engineering marvel of the entire paper.
Because obviously you can't load a 405 billion parameter model onto a single microchip.
Right, it would crash instantly. It's too big. So they had to slice the model up 4 different ways at the exact same time.
Let's break those 4 dimensions down.
Sure. Think of the whole setup like a giant factory with 16,000 workers. The workers are the GPUs, and you have one massive, impossible blueprint. That's the model.
Okay, I'm with you.
The first dimension is tensor parallelism. This is about splitting up the individual math operations. If the model needs to multiply two massive grids of numbers together, you literally tear that page of the blueprint in half. Worker A calculates the left side, worker B calculates the right side, and they glue the answer together.
Makes sense.
But that requires constant microsecond communication. So those workers have to be sitting physically right next to each other in the exact same server rack. You can't do that across the whole factory.
So what's the next split?
Pipeline parallelism. Think of the model like a multi-story building. Worker A processes the data through the first floor, then passes it up to worker B on the second floor, and so on. It's an assembly line.
Okay, so we're splitting the math and we're splitting the layers of the network. What's the third?
Context parallelism. Remember that huge 128,000 token context window?
The long novel.
Right. That's too much data for one worker to hold in their head. So you chop the novel into chapters. Worker A reads chapter 1, worker B reads chapter 2, and they pass notes to make sure they understand the full plot.
And the fourth dimension?
Data parallelism. That's just having multiple identical factory lines running the exact same model on completely different batches of text to speed up the whole operation.
So you're slicing the math, the layers, the context, and the data all at once across 16,000 chips. The synchronization required for that is, it's incomprehensible.
It's dancing on the edge of a knife. And that is exactly why the reliability section of this paper reads like a battlefield diary.
They were brutally honest about this. They monitored a 54-day snapshot of the training run, and they had 466 job interruptions.
466.
That's nearly 9 crashes every single day.
Every 3 hours, an alarm goes off in the control room. And they note that 78% of those crashes were purely hardware failures. A GPU burned out, a network cable failed, a piece of memory got corrupted. When you operate 16,000 of anything at maximum capacity, the probability of something breaking approaches 100%.
But the detail that absolutely blew my mind was the temperature issue.
Oh, the diurnal variation, yes.
They noticed that the training speed, the actual throughput of the data, was fluctuating by 1 to 2% depending on the time of day.
It's incredible. These data centers are physically enormous. During the hottest part of the afternoon, the sun beats down on the facility. The ambient temperature rises. The massive cooling systems have to work overtime, but the GPUs still get slightly hotter.
And what happens when a chip gets hot?
To protect itself from melting, the chip automatically dials back its power just a tiny bit. It's called dynamic voltage scaling.
So literally, the hot sun outside the building was slowing down the development of the AI inside the building.
It is the ultimate reminder that the cloud is not magic. It is millions of pounds of hot metal sitting in a room bound by the strict laws of thermodynamics.
Okay, so they battle the heat, they replace the broken cables, and finally they have a finished base model. But a base model just predicts the next word. It doesn't know how to chat or be helpful.
Exactly. Now we enter the post-training phase, and this is where the herd dynamic really shines.
Right, because standard post-training, using supervised fine-tuning and direct preference optimization, usually requires armies of humans writing perfect responses for the AI to learn from.
Which is incredibly slow and wildly expensive. So instead, Meta used that brand new 405B flagship model to generate millions of high-quality synthetic training examples for the 8B and 70B models.
The heavyweight champion training the amateurs.
Precisely. Those smaller models aren't just scaled-down versions of the big one. They are distilled versions. They punch way above their weight class because they've internalized the logic of the massive model.
But it's not just generating text. I want to highlight the coding section, because this technique, they call it execution feedback, is a huge leap toward actual reasoning.
It really is. It pushes the model away from just pattern matching and into actual problem solving.
Walk us through it. How do you use execution feedback to teach an AI to code?
Well, historically, you just show the AI a bunch of code and ask it to predict the next line, but code is tricky. I can write a script that looks perfectly formatted and uses all the right syntax, but if you actually run it, it crashes the whole system.
The story of every programmer's life.
Exactly. So Meta created a new loop. The system gives the AI a complex coding problem. The AI writes a solution. But then, and this is the crucial step, the system actually takes that code and runs it through a real Python parser and runs unit tests on it.
They treat the AI like a junior software engineer submitting a pull request.
Exactly. And if the code fails, The system takes the exact error message, like syntax error on line 42, and feeds it right back to the model. It says, you failed. Here is the error. Fix your own mistake.
And the model tries again.
It tries again. It debugs its own work based on the error. And once it finally gets it right, that entire process, the mistake and the fix, becomes the training data.
That is profound. It's not learning from a static textbook anymore. It is learning through trial and error.
Yes. And that feedback loop creates an incredibly robust coding model. Because it hasn't just memorized the right answer, it has experienced the process of finding the right answer.
Which naturally brings us to the model's capabilities. Because of this kind of training, the paper highlights that Llama 3 isn't just a chatbot anymore. It can use tools.
Yeah, it has a built-in search engine Brave Search and a Python interpreter.
So if I ask it a really obscure question about a current event, it doesn't just guess and hallucinate an answer.
Right, it has the self-awareness to recognize, I don't have this in my weights, and it will automatically generate a search query, read the web results, and summarize them for you.
But the Python interpreter is the real game changer for me. If I ask a large language model a multi-step math problem, like calculating a highly specific compound interest rate over 10 years, they usually fail.
Because they are trying to predict the numbers the way they predict words. They are doing math in their head, so to speak.
But Llama 3 does something different.
It essentially says, I'm not going to try to guess this number. I'm going to write a Python script that calculates compound interest. I will run the script using my interpreter. I will read the definitive output, and then I will give that to the user.
It reaches for a calculator.
Which is exactly what a smart human would do. It's shifting from knowing the answer to knowing how to acquire the answer.
They also spent a lot of time on multilingual capabilities. It fully supports 8 core languages now, including German, French, Hindi, Thai, and Spanish.
And the way they achieved that without making the English performance worse is really clever. They used a multilingual expert branch during training.
What does that?
Basically, they trained the model heavily on English, but then they took a copy of it and fine-tuned that copy exclusively on non-English languages until it was an expert. Then they carefully merged that expert knowledge back into the main model.
So it gets the benefit of the foreign language training without diluting its core English logic.
Exactly.
Okay, we have to talk about safety. Because you just described a massive AI that can write advanced code, debug its own errors, and search the live internet. The obvious fear here is, what happens when someone tries to use this to write a ransomware virus or, God forbid, design a biological weapon?
It's the most critical question in AI right now. Meta takes this very seriously. They actually released a completely separate model called Llama Guard 3, whose only job is to sit between the user and Llama 3 and filter out dangerous prompts and outputs.
But what about the underlying model itself? Did they test its potential for harm?
They ran extensive tests on what they call uplift. They wanted to know if having access to Llama 3 physically increases a bad actor's ability to cause harm.
How do you even test that?
You run controlled studies. They took groups of people, some novices, some actual security experts, and tasked them with planning cyber attacks or outlining biological hazards. Half the group was only allowed to use a standard internet search engine. The other half was given unrestricted access to Llama 3.
And the results? Did the AI group become supervillains?
The paper explicitly states there was no significant uplift.
No significant uplift. That's a very careful phrase.
It is. What it means is that Llama 3 definitely helped them organize information faster, but it did not give them any actionable capabilities that they couldn't already find just by using Google or reading publicly available papers. The danger is already out there on the open web. The model just summarizes it.
That is reassuring. Though I imagine it's an endless cat-and-mouse game.
Yeah.
The paper talks a lot about their red teaming efforts, where they hire experts to try and break the model's safety guardrails.
Yes. And a massive focus for this model was defending against something called many-shot jailbreaking.
I've heard of this. This is because the context window is so big now, right?
Exactly. With the 128,000 token window, an attacker can paste in hundreds and hundreds of fake theoretical conversations where the AI is happily helping them build a bomb.
So they essentially flood the AI's short-term memory with bad examples.
Right. They overwhelm its safety training by creating a false reality where breaking the rules is normal. They had to spend a significant amount of post-training compute, specifically hardening the model to resist that exact kind of psychological pressure.
Hypnotizing the AI, basically.
Pretty much.
Before we wrap up, I want to quickly touch on the future. There is a section near the end about multimodal capabilities. vision and speech.
Which are still under development, according to the paper. They haven't broadly released them yet.
But the approach they're taking is really interesting. They call it a compositional approach.
Yeah, instead of training one gargantuan model from scratch to understand text, images, and audio all at the exact same time, they took the Finnish Llama 3 text model and basically bolted on an image encoder and a speech encoder.
Like attaching eyes and ears to a brain that already knows how to think.
Exactly. It's a highly modular approach. And the advantage there is that a year from now, if they invent a much better vision encoder, they can just swap out the eyes without having to spend millions of dollars retraining the entire text brain.
It's incredibly practical, which really feels like the theme of this entire paper. So we've covered the specialized herd, the annealing data, the melting GPUs, and the self-debugging code. When you step back and look at all of this, what is the one big takeaway for you?
For me, it's a very specific realization they had regarding the smaller models, which challenges a fundamental rule of AI called the chinchilla scaling laws.
Oh, this is the provocative thought I wanted to end on. Unpack the chinchilla laws for us.
Basically, the chinchilla formula tells you the mathematically optimal amount of data you should use to train a model of a specific size. The law says that if you train the model past that optimal point, you get diminishing returns. It's supposedly a complete waste of compute.
But Meta ignored the law.
For the smaller 8B model, yes. They trained it on vastly more data than the chinchilla formula says you should. They trained it way past the point of diminishing returns.
And did it waste compute?
Well, yes, it costs more to train, but the model kept getting smarter. It didn't plateau the way the law predicted.
So the established law of AI scaling was just wrong.
Not wrong, just incomplete. The chinchilla law optimizes for training efficiency, how to get the smartest model for the cheapest training cost. But Meta isn't optimizing for training. They're optimizing for inference efficiency.
Inference meaning when the user actually runs the model on their phone.
Exactly. Meta realized that if this 8B model is going to be downloaded and run billions of times on laptops and smartphones, it is absolutely worth spending a fortune up front to overtrain it. You force a massive amount of knowledge into a tiny footprint.
So you spend the money once in the data center, so the model is lightning fast and hyper-competent on my phone.
Precisely. And that is a huge shift in the industry's mindset. It suggests that the future isn't just building bigger and bigger monolithic models. The future is taking very small models and aggressively overtraining them to absolute perfection.
A herd of small, hyper-competent experts living right on your device instead of one giant god in the cloud.
That's the vision.
That is a fascinating place to leave it. For everyone listening, it's definitely worth considering how these localized, specialized herds are going to change the software you use every day. The era of the monolith might really be ending. Thanks for diving into this absolute beast of a paper with us.
Oh, always a pleasure.
We'll see you all in the next deep dive.